Okay, so we have a combustion analysis problem here, and the problem's already written out here, and it's kind of dense text. We have 4.24 milligrams of this compound, and we're going to burn it. That's the combustion analysis. So we've got this reaction chamber here. We put this stuff in here, and we burn it up, and the gases that come off kind of come through this pipe, and then we have a little chamber in here, and then it's going to go through another pipe, and we got another chamber, and then the stuff goes out here and goes off somewhere where the rest of the stuff gets caught. Now, the point of this is that we are going to have in this first chamber, this thing has something which we can use to collect the water that is produced by the combustion. And in here we have another something that's going to collect carbon dioxide. The point of this is that I should have put here a pipe at the beginning where we have oxygen going through, because if we're going to burn something, we need oxygen going through. And the oxygen stream also brings the gases that are produced from the combustion through this whole series of pipes and chambers, so that any water that's produced by the combustion reaction will be collected in this first chamber. Any carbon dioxide that's produced will be collected in the second chamber. When we burn an organic compound, you're going to have the fuel, you're going to have the oxygen, and what you're going to make is water and carbon dioxide. From this organic fuel, which has carbon and hydrogen and maybe some oxygen in it, the carbons all end up in carbon dioxide, and the hydrogens all end up in the water. So if we weigh this little kind of water sponge in this chamber here, in the first chamber, the collection chamber, if we weigh that before the combustion and then after the combustion, the water that is trapped in that sponge is going to be the difference in the mass between the before and the after. And so we'll know how much water was produced by the combustion. Same thing for the next chamber. We're going to weigh that sponge, that collection device, before and after, and the mass difference between the before and after picture is going to be how much carbon dioxide was produced. So then we kind of work backwards to figure out how much carbon and hydrogen was in our fuel. So let's do it with this problem. We came up with 6.21 milligrams of carbon dioxide. That's how much was formed. We want to figure that out in terms of just the carbon. We want to know how much carbon was in our fuel to start with. So let's just change the milligrams to grams, and then we're going to do a ratio that is similar to percent composition, where we say, oh, out of 44.0 grams of carbon dioxide, actually that would be 44.01 if we wanted to be even more precise. Out of that, 12.01 grams are due to carbon. The others are due to oxygen. Now, the oxygen could be, that oxygen in the carbon dioxide could be from the original compound, or it could be from the oxygen that it reacted with, coming through the stream of oxygen being fed into the chamber. So we don't know about the oxygen, where it came from, but the carbon all had to come out of that compound to start with. So we can use this to figure out exactly how much carbon there was in our original sample. So we're going to do that calculation and come up with 0.00169 grams of carbon. So we know out of our original 4.24 milligrams of our sample that of that 169 milligrams were due to the carbon. Okay, so let's go on to the next one. We have 2.54 milligrams of water. All right. So let's do the same thing here. Change the milligrams to grams, milligrams to grams, and in this case we have to deal with water, so 2.02 grams of hydrogen are in every 18.02 grams of water. Now, where did I get these numbers? This is just the molar masses adding up on the periodic table. We'll say we don't have 44 grams of carbon dioxide. We don't have 18 grams of water, which are in these conversion factors here and here. But if we had 18 grams of water, of that, 2 grams would be hydrogen every single time. And so we can use that ratio to figure out of our sample how much was hydrogen. So let's do that, and we will come up with 0.000282 grams of hydrogen. Okay, moving right along. We've got carbon, we've got hydrogen, and we also know that in our original sample there was carbon, hydrogen, and oxygen present. And we also know that our original sample was 4.24 milligrams. So converting that into standard notation, we have 0.00424 grams of our compound. But we know, we just figured out, that of that, 169 grams were carbon, and also 282. That's the number of grams of hydrogen. So if we subtract both of those away from this, we can find out the result. The rest of it has to be oxygen. There's only, back to our problem, looking back up at the top, it says only carbon, hydrogen, and oxygen was in the compound. And so we just figured out how much carbon there was, we figured out how much hydrogen there is, and the rest of it has to be oxygen. So we have 0.00227 grams of oxygen. So now we have where you often start in a problem for empirical formula. We know how much of each of the elements we have. So that was the first part of the combustion analysis problem. Now we have to keep going because we're going to move into the section where we're going to kind of do the normal empirical formula kind of thing, and I'm going to go on to the next page for this part because I'm running out of space on that page. So now we're going to look for the empirical formula. So I'm going to take my three numbers that I found, 0.00169 grams of carbon, 0.000282 grams of hydrogen, and 0.00227 grams of oxygen. Each of those are nice, useful numbers, except for that they won't tell us the ratio of carbon, hydrogen, and oxygen in the compound because, of course, carbon atoms, hydrogen atoms, and oxygen atoms weigh different amounts, and so it's not going to be terribly useful for us to have grams. So what we want to do here is just convert this into moles, which is pretty simple to do. 12.01 grams of carbon is 1 mole of carbon, and we have 1.008. Sorry, putting it on the wrong. Let's get rid of that. Okay, trying to talk and write at the same time. I guess it's being challenging right now. 1.008 grams of hydrogen. But you can always just cross stuff out and keep going. All right, so we're going to change oxygen to moles also, 16.00 grams of oxygen. And now I'm going to just go ahead and multiply these numbers, and I'm going to end up with some moles. So 0.000141 moles of carbon. Of course, you could be writing this in scientific notation if you didn't want to just write down all these zeros, but I just thought for this particular example I would do it this way. Moles of hydrogen and 0.000142 moles of oxygen. So now I have my moles. So out of our original 4.24 milligrams of our sample, we now know in that particular little sample how many moles of carbon we have, how many moles of hydrogen we have, and how many moles of oxygen we have. That's useful because moles are proportional to the number of atoms. Moles is just a counting unit that has a bunch of things in the group, but the bunch, the number, the amount is the same for every mole, for every element, for anything that you count in moles. So to get the empirical formula, we're going to look at these number of moles. And I'm going to say, hey, let's divide them by the smallest number. Now, I hope that you can follow me if I don't bother to write down all of those zeros. I'm going to look at this and say, look, I've got 1, 2, 3 zeros here. I've got 1, 2, 3 zeros there, 1, 2, 3 zeros there. So since it's the same, since they're all in the same place value, I'm not going to bother with putting all the zeros down. Now, if there were different numbers of zeros, we would absolutely have to. And if you're not really sure what you're doing, then I would encourage you to write down the whole number. But this will work. So 142 divided by 141. What am I doing here? I am dividing all three of them by the smallest number. And this is my number for carbon. This is for hydrogen. This is for oxygen. 141 was the smallest of my three numbers. Actually, it was 0.000141, but we dropped all those zeros out because they're all the same, and they would cancel top and bottom anyway. So my empirical formula is now determined, right? We know what the empirical formula is. We know that for every carbon, we have 2 hydrogens and 1 oxygen. And even though this is 1.99, that's really, really close to 2. And 1.01 is really close to 1. You can do this if they're really close, like within a couple hundredths. If this turned out to be 1.8 or 1.7 or 1.3 or something like that, no way could I round that off, because it probably means it's a much bigger integer ratio. But 1.99 is really close to 2, so we can count that as saying, okay, for every carbon we have 2 hydrogens. Now, going back to our original problem and looking at it, it also, besides the empirical formula, wants us to find the molecular formula. So in order to do that, I need the molar mass. So we know that the molar mass of the compound, and I'm just going to abbreviate compound CMPD, you'll know what that means. It means compound, okay? Is 60.0 grams per mole. And our empirical formula that we've determined here is the molecular formula if it weighs 60.0 grams per mole. So we have to determine that. So let's find out. The empirical formula is C is 12.0 grams, because I'm adding this up off the periodic table. 2 hydrogens would be 2.0 grams, and an oxygen, 16.0 grams. And what am I going to get? Because I'm adding up, I'm going to come to the nearest 3 sig figs, and look at that. 30 grams is not equal to 60 grams. So our empirical mass, the empirical molar mass, is not equal to the molar mass of the compound. So we have to look for a ratio of the two. So I'm going to take the bigger one, molar mass, which is grams per mole. I'm going to divide it by the smaller one, 30.0 grams per mole. And of course you've already done this in your head, but just in case the numbers aren't quite as easy as 60 over 30, I want to show you how it's done. We take the bigger one over the smaller one, find out what the ratio is. The ratio is 2. So what we've just found out is that the compound weighs twice as much as what the empirical formula would lead you to believe, which means we have twice as many atoms of everything. So we're going to take CH2O times 2, because there's twice as many of everything. So that would be C2H4O2. So this, yay, we are finally to the answer. This is our molecular formula. This could be acetic acid. It could be a couple other different compounds. We would probably go on in a lab to say, let's now figure out what the structural formula is, exactly which atoms are connected to which, where are the oxygens located in the compound. But our problem so far just asked us to get to the molecular formula. So we've gotten to the molecular formula. We have triumphed. We are at C2H4O2, and that is our final answer.